Assalamualaikum everyone. So today we want to talk about application 6.1, which is about visible flow problem. So as we can see, the visible flow problem requires that we identify a flow X in a network G equal to NA, which is N for nodes and A for arcs. So this satisfies the following constraint, which is the constraint is when sum of xij minus sum of xji equal to bi, where for I it belongs to n, which is nodes, while the second constraint is 0 smaller than xij and smaller than uij, where for all ij it belongs to A, which is A stand for arcs. So we proceed to the theory, which is as before. We assume that sum of bi is equal to 0. So we introduce two new nodes as a source node S, as a source of node S, and a sink node T. So sink node T, we put this node T, and also for each node I with bi is larger than 0, which is each node I, which is I can put I here, with bi is more than 0, which is bi is larger than 0. Okay, so we add an arc Si with a capacity of bi. So we add Si as a capacity of bi. So we put it here, and the capacity is bi. So we put this bi here, which is the capacity from node S to node I. So the node is for each node I with bi is smaller than 0. So we add an arc IT, so IT with a capacity of negative bi. With bi, we refer to the new network as the transform network. Then we solve a maximum flow saturates all the source and sink arcs. So by this, it is easy to verify why this algorithm works. If X is a flow satisfying from constraint 1 and constraint 2, the same flow with X as I, which is X as I is equal to bi and X IT is equal to negative bi for each sink R, I, and T. Is a maximum flow in the transform network since IT saturates all the source and the sink R. Similarly, if X is a maximum flow in the transform network that saturates all the source and the sink R's, this flow in the original network satisfies both of these constraints here. Therefore, the original network contains a visible flow if and only if the transform consists of flow that saturates all the source and sink arcs. So we proceed to the example, which is we must take note something before we continue to do a visible flow, which is first is an arc can exceed its capacity, and the second is the flow in must be same as the flow out. So for example, this is a capacity flow. Here we can see the capacity flow. The capacity flow we need to change into the visible flow. Here, visible flow. So this is an example of capacity flow, and we need to change into the visible flow network. So with these two nodes, we can do the visible flow network. So as we can see, we need to maintain the minimum of capacity. So we put it here, 5 and 5. So here we put here in, for example, I put it 10. So here we can see the ingoing of capacity is 15. So the outgoing capacity must also be 15. For example, I put here is 5, so the other one is 10. So the next is, what if, so if I put here 10, so the ingoing capacity is 10 and the outgoing must be equal to 10 also. So if here is 5, then here must be 5. So the ingoing of A to C is 5, so the outgoing must be 5 also. So here I will put as 0, and here I put as 5. We can compare the capacity network and visible flow network. So the next is I want to explain you guys about saturated. Saturated is because of, in here for example, I put SB, amount of SB is 10, and it's the same of amount of in capacity network, same goes. So this is we call as SB is saturated. So the next we can ask about the flow, which is we can see about SACT. Here you can see SACT. So we can ask about the flow of along SACT, just because we got 10, 5 and 5, so we go for 5 because the 5 is the smallest number along the SACT. But when we talk about the maximum flow through the capacity, SACT here, SACT, we go for 10. Because the 10 is smallest number between SA is 20 and AC is 20 and CT is 10. So we go for 10.